Hello, in this video we're going to be talking about the first derivative test, which uses the derivative to determine whether we have a maxima or a minima at an extrema. So what it does is it checks what is going on with that first derivative. If we change from positive to negative, that's maximum. If the derivative changes from negative to positive, then we have a minimum. But if the derivative does not change signs, like it's positive positive or negative negative, then that is not going to be an extreme value. It's where the derivative kind of lies to us a little bit. Let's take a look at an example. So I want to first find the critical numbers of this thing. I've already done that. There we go. Done did it. Found the derivative, found when that derivative equals 0. These are our potential extrema of our function. So then we need to figure out what are the intervals where the function is increasing or decreasing. Done that already. So our original function, our derivative first is positive and then is negative, and then it is positive again. So our original function goes from increasing to decreasing to increasing. Now that we know our intervals of increasing and decreasing, we can apply the first derivative test. We can see here that derivative changes from positive to negative at this point. So we are increasing and then decreasing on the original, making this point a maximum. I got this 20 by plugging in this -2 into the original function. What we can do next is we can see here that we have a negative first derivative and then a positive one. So the original is decreasing and then increasing, meaning that we have a local minimum at 1. Again, I got this -7 by plugging this 1 into the original function. We can check that on our graphing utility. Already done did that. So you can see this is the graph of the original function, and at -220, we have that maximum, and at 1, 7, we have that minimum that we were told by that first derivative test. In this example, we're again looking for those extreme values. I've rewritten the problem a little bit here, and then I found the derivative using the chain rule, and then kind of cleaned up the problem a little bit, because that's not what this video is about. It's about finding these extreme values. So there are different places where this thing is going to have some trouble. In the numerator, at x equals 0, we're going to run into trouble because, it's just going to make that derivative equal to 0. We also have trouble down here if that is plus or minus 1. If x equals plus or minus 1, then we would have 0 right there. Not right there, but in all of that, and we'd have a 0 in the denominator. So those are critical values. This one's a little unique because if we think about these two critical values, if we tried to plug them in up here, again, we would have 0 in the denominator. So plus or minus 1 is not in the domain of our original function, so it's not a point on y. So now we just need to figure out what is going on with that derivative around 0. If I plug in a number that is less than 0 into my derivative down here, in the numerator, we'd get a negative number. In the denominator, let's see, if I would put in something like -10, you square that, subtract it from 1, that's negative. If you put that to a 4/3 exponent, that'll make it positive because something to the fourth would be positive. So we really got something that is negative over something that is positive. So overall, this derivative is going to be negative over here. If we try to put something positive into this thing, we would get a positive value up top, and then kind of like following that same logic on the bottom, if we square that positive, it's going to be a positive value, and subtract it from 1, do it to the fourth, all that stuff. We're going to end up with a positive over a positive. So this thing overall is going to be positive. That means y is switching from decreasing to increasing. I need to get out of the way. Decreasing to increasing at that point. If we are going from decreasing to increasing, or our derivative is going from negative to positive at 0, we should have a minimum value. And we can plug 0 in to find it. So by the first derivative test, there is a local minimum at 0, 1, since the derivative changes from negative to positive at x value of 0. Done. In this example, I want to find the extreme values where they occur. So I've already taken the liberty of finding the derivative, and I've solved it a little bit so that it's easier to figure out when that derivative equals zero. So now that it's in this factored form, I can tell that it equals zero, at x equals -3, and at x equals 1. Now that I know that, I just need to figure out what is happening to that derivative on either side of those numbers. Those are my critical points. So what's going on around them? I'm going to map them out on this number line, space them as I please, and see what is happening to our derivative. If we do some really large value, this will definitely be positive, and then this will be positive, and then this will be positive if we have a very large value for x. So that means this area over here will be positive for that first derivative. If we do some value between 0 and 1, like a half, then this will still be positive. This will also be positive, but if we do a half minus 1, this piece right here will be negative. So a positive times a negative. Overall, this thing is going to be negative. If we try to do a value in between here, like -1, then this is going to be negative, this is going to be positive, and then this is also going to be negative. So a negative times a negative, overall, in there we are going to be positive. Finally, if we do a huge negative number, then this is going to be negative. It'll outrun that +3, so that'll be negative, and then this will also be negative. If you multiply three negatives together, we end up with a positive. I mean a negative, sorry. So we can see that we're kind of bouncing back and forth. So here where we're decreasing to increasing on the original function, this one should be a minimum. Same thing over here. We should get a minimum value. And then when we're shifting from going up to going down, a positive derivative to a negative derivative, increasing to decreasing, this is a maximum. All of that by the first derivative test. Now that we know that which ones are maximums and which ones are minimums, it's just a matter of plugging these critical numbers into the original function to see where those minimum and maximum are. And I'll take care of that. So by the first derivative test, y has a local minimum at 0, 10, and local minimums at -3. I converted this into a fraction, and 1, 6.5, because I just like fractions. I could go in more details about that, but I also noticed that this thing didn't ask me to justify my answer, so I didn't want to do it. So I didn't do it. And that's okay. Now, there's another part of the first derivative test, and that is what is going on at the endpoints. The examples up to this point have not had endpoints, so I've not talked about this, but it is important for us to know. This is the actual technical definition of it. This is kind of more what I want you to be thinking about in terms of this, grid. If we have a decreasing function, a negative derivative, if we're looking at the left endpoint, you can see that's like a maximum. But at a right endpoint, that is going to be a minimum if we're going down on our original function. If our derivative is positive, so our original function is increasing, you can see here that on the left-hand side, we end up with a minimum, but at the right-hand side, we get a maximum. This is that same thing in words, but I can't track this, but I can track this table. So it is up to you which one makes more sense for your head. In this example, we are looking for extreme values. We do have endpoints this time. It also mentions extreme stationary points. It's something weird that Finney has, that it's just when the derivative equals 0. If something like that were to show up on the exam, they would define a stationary point for you. So let's figure out when this derivative is going to equal 0. So the only time this thing would equal 0 is, well, never, because that numerator can't be 0. So that can't equal 0. Can it break? So can e to the x ever equal 0? Well, no, that doesn't matter either. So because you can't get e to the x to be 0. So there are going to be no critical values for this thing. However, the first derivative test says, hey, you need to check these endpoints and see what's going on there. So we need to check them for maximum and minimum. This derivative is always negative. We can see right here that it has got a negative value. So no matter what, we're spitting out negative values on this function. So on this derivative, so the original function is like decreasing in some way, shape, or form. That makes this x value of -1 to be a maximum and that x value of 1 to be a minimum, which is what was shown on that table that we had before, that if we've got a left endpoint and we are decreasing, we'll get a maximum. And if we have a right hand endpoint and we are decreasing, we get a minimum. So now it's just a matter of figuring out what that is when we plug that into the function. I'll take care of that. So by the first derivative test, we get a maximum value of e when we plug into the original function and a minimum value of 1 over e when we plug this value into the original function again. So even though we're just checking these endpoints, it is still it's still using the first derivative test. It's just the other half of it. In this example, again, we're looking at not stationary points, Finney, and you can kind of see why Finney is talking about this in this example. The first derivative test cares about checking those endpoints. And when we get to this one, these are minima on this function or maxima, but it doesn't matter because those are stationary points where the derivative equals 0. Really, this question is testing, do you know that second half of the derivative test to check these endpoints as potential maximum or minimum? By putting this information about not stationary points, it makes it so this problem is just looking at these two endpoints. Since these two endpoints do not exist in our original function, what they're looking for has nothing. So they want a kind of like a nothing answer and not a question that was just talking about these specific maximum and minimum. That is the end of our video on the first derivative test. A reminder that if our derivative is changing from positive to negative, we get a local maximum. If we are changing from negative to positive, we get a local minimum. Be careful about whether or not the first derivative doesn't change sign at all. If that ever happens, you do not have an extreme value. I didn't show that in this video because it's just like, well, it didn't change, so nothing. There's also this right and left endpoint thing. This table is a representation of what was written in text when we had that slide. And that's it for our first derivative test. Thank you for watching. I hope you took some good notes, and I'll see you next time. Bye-bye.